All right, so for today, we're going to be covering polynomial functions. So a polynomial is a mathematical expression that is the sum of terms, where each term contains only variables with whole number exponents and integer coefficients. So for example here, now this is considered a term, is a 9x to the fourth power. Okay, the coefficient is a number that's in the front. Okay, your variable is the letter, which is the x, and then the exponent here is 4. Okay, so it's 9x to the fourth power. That's the first term. The second term is going to be 2x to the third power. So it would be 2x to the power of 3. You have your coefficient, you have your variable, and you have your exponent. The next one is going to be the negative 7x squared. So because of the minus, we do treat that as a negative 7x squared. That would be the term. The negative 7 would be the coefficient, the x would be the variable, and the squared would be the exponent. All right, so next here we have 5x. So 5 would be the coefficient, x would be the variable, and then the exponent is 1. Now the 1 is understood that it's to the first power. Okay. And then the last term here we have is just the minus 3, okay, which is just the coefficient, no variable, no exponent. Okay, and it should be x to the 0 power. And remember, anything to the 0 power is just 1, right? So that's why they don't put it in there. It's just negative 3. All right, so the terms are, so I'm going to go ahead and write up all the terms. So 9x to the fourth power, 2x to the third power, negative 7x squared, 5x, and negative 3. So the variables with whole number exponents are, so the variables are x to the fourth power, x cubed, x squared, and x. Those are our variables with the whole exponents. Okay, the coefficients of these are, our coefficients are 9, 2, negative 7, and 5. And then the constant term is negative 3, the one by itself. That's what it's talking about here, negative 3. Okay, so here we have 9. It's a coefficient of x to the fourth power. We have 2, that's a coefficient of x cubed. We have negative 7, that's a coefficient of x squared. And then we have 5, that is a coefficient of x. Okay. So now, the standard form of a polynomial is writing the terms in descending order according to the exponent. So we are going to write in standard form. The degree of the polynomial. So whenever they ask you for the degree, is the same as the greatest exponent. So you look at your equation. So in this example here, the greatest exponent, the biggest exponent was this one, the x to the fourth power. So your degree here of your polynomial is 4. So we will call this a degree 4 polynomial. Okay, the leading coefficient is a coefficient of the term with the greatest exponent. The leading coefficient of the polynomial in this example is, so we have 9x to the fourth power. Okay, that's the first one that's in front of the entire equation that we have here. We already said that because of this 4, that's how we say that this is a degree 4 polynomial. Now the leading coefficient is a number that's in the front. So the number in the front of this one is 9. Okay, that's called the leading coefficient. It leads the entire equation. Okay, so here we have our polynomials in standard form already for us. They want us to put the degree and the name, how many terms we have, the constant term, the leading term, and the leading coefficient. Polynomial is a first degree polynomial, okay, because the x is to the first power. So the degree is 1. And so the name of this, whenever it's a first degree, this is a linear function. Linear. Okay, so the number of terms that this one has is 1, 2. It has 2 terms. Okay, the constant term, which is the number that's by itself, which is this one here, is 3. The leading term, which is the 2x, which is in the front. And then the leading coefficient is the number in the front, which is a 2. Okay. All right, let's try the next one. So on this next one, we have negative x squared plus 4x minus 5. So it is a second degree polynomial because of the 2 here. And so whenever it's a second degree, this is actually a quadratic equation. Okay, and the number of terms that it has 3 terms. So 1, 2, and 3. So 3 terms. The constant term, which is the number that's by itself at the end that doesn't have any variables, is -5. And then the leading term is -x squared, the one in the very front. Okay. And then the leading coefficient, which is a number in the front. Now remember, there's no number here in the front, but we do know it is an invisible one, so -1. All right, the next one. Okay, so this one is x to the 3rd power. So this is a 3rd degree polynomial, which makes it a cubic polynomial. And so because it is a 3rd degree, the number of terms that this has is 1 and 2. So here I'm going to put 2, and then the constant term is 4. I'm sorry, not 4. I was already getting ahead of myself. The constant term, there's no constant term. There's no number here in the very end that's by itself. So it's going to be none. Okay, the leading term, the one that's in the front, is 4x to the 3rd power. And then from there, the leading coefficient, which is a number in the very front, is 4. Then we move to the next one. We have 6x to the 4th power plus x cubed minus 5x squared plus 3x minus 1. Okay, so this one we have 1, 2, 3, 4, and 5. So it has 5 terms. Okay, the highest exponent here is 4. So this is a 4th degree, and this is called quartic. Quartic. Like quarters, quartic. Okay. The constant term, which is a number by itself, is this one at the very end, which is -1. The leading term is a 6x to the 4th power. This is leading the entire equation. And the leading coefficient here is 6. Okay, then we move on to the next one. So here we have 9x to the 5th power plus x cubed minus 1. Okay, so this is the 5th degree. Okay, and then I hope I spell this right. This is a quintic. Let me just make sure real quick. Yes, okay. Quintic. Okay, so it is a quintic, and then this is a number of terms would be 3. And so here we have the constant term is -1, which is a number at the very end by itself. Our leading term is 9x to the 5th power, and the leading coefficient is 9. Okay, so let's go ahead and try some on our own. It says rewrite each polynomial in standard form, then identify the leading coefficient, degree, and number of terms of each polynomial. Okay, so first we need to write this in standard form. So we write it f of x equals. And then we start with the highest degree. So the biggest one here is x to the 3rd power. And then the next one would be the x squared, but it does say minus x squared. So I'm going to put here minus x squared. Then we have the 2x, so plus 2x. It's a positive 2x, that's why I put the plus. At the very end, we have minus 5. Okay, so this is a 3rd degree polynomial, and our 3rd degrees are cubic. Okay. The number of terms, we have a total of 4 terms. The constant term is -5, which is a number by itself. The leading term, remember, if there's no number here in the front of the x cubed, it is an invisible one. And then the leading, it's 1x to the 3rd power. The leading coefficient is a 1. Okay, let's go ahead and move on to the next one. So we're going to write this one in standard form. The 3x to the 4th power is going first, then the 5x squared minus x. So we go from the biggest degree to the smallest degree. So this is a 4th degree polynomial, which we call a quartic. Okay, the number of terms that it has is 3. The constant term, there's no constant term, none. And then the leading term is 3x to the 4th power, the one that's leading in the front. So the leading coefficient here is 3. Okay, so now the graph of a polynomial functions are smooth and continuous, no breaks, no holes, no sharp turns. The end behavior of the graph of a polynomial function is the direction of the graph as the x values approach negative infinity and positive infinity. Okay, so the way that you're able to tell what your graph is going to look like is you first start off by seeing, is the degree of the polynomial even or is it odd? Okay, so you have those two options. Now, if it is even, then your leading coefficient, it tells you here, the leading coefficient is, now your leading coefficient can either be positive or it can be negative. Okay, positive or negative. And then the same here. Even if it's an odd, your leading coefficient can either be positive or negative. Okay? And so they give you some examples of this. So even functions that have a positive leading coefficient would look like this. This is x squared, that would be an even degree. This is x to the 6th power, that would be an even degree. And if you look at the leading coefficients, they are positive numbers, 4 and 2. Okay, so whenever it's positive and it's even, your end behavior at your graph is going to be pointing up in both directions, up. Okay? So if it's even, your arrows are going to go in the same direction. Either they're both going to be going up or they're both going to be going down. And when they go down, that is when your leading coefficient is negative. Okay. Now for odd. Okay. If we look at here, if our degrees are odd, so here are some examples of when our degrees are odd. So here we have 3, we have 7, we have 5, and we have 9. Okay, so those are odd degrees. And so whenever we have odd degrees, we need, our arrows are going to go in opposite directions. So opposite directions are our end behavior, opposite. Okay, so if it is positive, okay, so it's an odd degree, but the leading coefficient is positive, then our graph is going to be going up at the very end. It starts down first, but it's going to go up at the end. And if it is negative, it's going to start up, and then it's going to be going down at the end. Okay, so that's how we're able to do our end behavior. So this one would be starting up, but then at the very end, it goes down. But when it's a positive coefficient, it's going to start at the bottom and then rise up. Okay, so here it says, analyze the end behavior of the following graphs and determine if the degree of the polynomial graph is even or odd. Also determine if the leading coefficient is positive or negative. So if we look here, first, if we notice the end behavior, it is starting up, but then it goes down at the end. So because the arrows are pointing in opposite directions, the degree of f of x is odd. And the leading coefficient is, because it is pointing down at the end, it is negative. Negative. Now, there are blank real zeros and blank relative maximums. So zeros is where your graph crosses the x-axis. So right here, there's 1, 2, and 3 real zeros. And relative maximums, so since they're asking for the maximums, we're looking for a little peak, like a little top of the hill. So if you see right here, there's a little top of the hill right here. That is a relative maximum, and that's the only one. So there's one relative maximum. Okay, moving to the next one. The degree of f of x is, so if we look at the end behavior here, we're going to notice that our graph is pointing up at the very end, and they're both pointing up. So since they're both in the same direction, it is an even function, or an even degree, sorry. And the leading coefficient is positive or negative. So because they're both pointing up, it is positive. Now, there are blank real zeros. So we have 1 and 2. There are 2 real zeros and blank relative maximum. So we're going to look for a little peak or a little top of the hill. So if we look here, our graph, it goes down, and then it goes up, and then up again. So it doesn't even look like it has any maximums because it never reaches like a little, we're looking for a little swoop like that. And we don't see that. So it has 0 relative maximums. Okay, the next one. So if we look at this one, our graph for our end behavior is pointing down in both directions. So the degree of f of x is even because they're both pointing down, okay? And the leading coefficient is, because they're pointing down, the leading coefficient is negative. There are blank real zeros, so let's go ahead and see how many times does it cross the x-axis? It crosses 2 times, so 2 real zeros and blank relative maximum. So like I said, we're looking for the little top of the hills. So we have 1 and 2 top of the hills, so 2 relative maximums. Okay, the next one, the degree of f of x is, so if we look at the end behavior, it is pointing down here, but up here. So because the arrows are pointing in opposite directions, this is an odd degree, okay? And the leading coefficient is, now because at the very end it is pointing up, our graph, reading it from left to right, it goes up. This is positive. There are blank real zeros. So how many times does it cross the x-axis? It crosses 1, 2, and 3 times. So there are 3 real zeros. And how many relative maximums? So remember, we're looking for a little peak, a little top of the hill. So the little peak here, this is only one. We have 1 relative max. All right, so a few more. This one is asking us for the degree. So the degree of this, we look for the highest exponent, which is 4. What is the sign of the leading coefficient? So the leading coefficient is this number right here in the front. So the sign is negative. Okay, so I'm going to sketch the graph really quick. And so on here, since it's an even degree, that means it's going to be pointing in the same direction. Because it's negative, that means it's going to be pointing down. So it's going to be down, down, and who knows what this graph looks like. It looks something like that. So the end behavior, this is the way we write our end behavior. Okay, so it's going to be as x approaches negative infinity, f of x approaches, and then this is the part that's going to be different, okay, for every problem. And then this part's going to be as x approaches positive infinity, f of x approaches, and then this is a part that is also going to be different, okay, for every problem. The rest of it, you're going to copy it down for every single one of them. It's going to be the same thing as x approaches negative infinity, f of x approaches, and I'll explain right now what it means. So as x approaches positive infinity, f of x approaches blank, and we're going to fill that in. So I already drew my graph here. Okay, so the way that it's saying x is approaching negative infinity, it's saying the negative x values over here. Where's our graph going? So on this side of our graph is pointing down. That means that our graph is pointing down to negative infinity. Okay, this one's saying when x approaches positive infinity. Okay, that means it's talking about this side of the graph, the right side of the graph. So on the right side of the graph, our arrow is pointing down as well. So that means it is also approaching negative infinity. Okay, so let's try the next one. This is a degree 5 polynomial. Okay, this is an odd number. I should have wrote that on this one. I should have put even here. The sign of the leading coefficient. So the leading coefficient is the number in the front. This is a 2. Okay, it is a positive number, so it's positive. Okay, so because it's odd, it's going to be pointing in opposite directions, and because it's positive, that means our graph is going to be going up. So it'll look something like that. Okay, so if that's what our graph looks like, as x approaches negative infinity, so remember I told you guys that's talking about the negative x values, which would be on this side, our graph is pointing down, so it would go to negative infinity. Okay, on the right side, our graph is pointing up. Okay, so that means that f of x is approaching positive infinity. Our function is going up to the positive infinity. Okay, so we have 2 more examples of this, just in case you didn't get it. So the first one, it wants to know what's the degree of the polynomial. So we look for the highest exponent. The highest exponent is a 3, and 3 is an odd number. Okay, the sign of the leading coefficient. So the number that's in the front is a -3, so it is negative. Okay, so because it's odd, that means our arrows are going to be pointing in opposite directions. And because it's negative, our graph is going to go down. Okay, so like I said earlier, you're going to have as x approaches -infinity, f of x approaches. And then that means on the left side of the graph right here, our graph is pointing up. So it's pointing up to positive infinity. And then we write the next one as x approaches positive infinity. So that means that when your x values are positive, which is on the right side, your function f of x is going down. So it is approaching negative infinity. Okay, so let's go ahead and move on to the last example here. So we have 3x to the 6 minus 6x squared minus 8. The degree is 6. This is an even number. The sign of the leading coefficient, the number in the front is a 3. This is a positive number. So the end behavior. Okay, so I'm going to go ahead and write this as x approaches negative infinity. As x approaches positive infinity, our function approaches Okay, so here we said it was even, so that means that they're going to be pointing in the same direction, and it is positive, so that means that they're both going to be pointing up for our end behavior. Usually it's just like a little W on the bottom or some little shape like that. And so since it's pointing to the top on the left side, so this part is going to go up to positive infinity, and then the part on the right side is also going to positive infinity. So that's what we put here. And that's it. Thank you guys.